Quick scenario. You order a pizza. The app says 10 minutes based on how far the store is from your door.
But is distance really the whole story? 2 orders, same distance. One shows up in 10 minutes, the other in 25.
Because distance isn't the only thing that matters. One predictor was a start. It just wasn't the whole picture.
And that's exactly where we pick up today. Last time, Lecture 18, we predicted one number from another, a final exam grade from a midterm score. Today, what happens when we use 2 predictors instead of 1? This is a bonus episode, off the main sequence, straight from the textbook. Multiple linear regression.
Look at the picture. Distance from the store to your door. Farther away tends to mean a longer wait. That's a real useful predictor.
But here's what it leaves out. How many other orders are already ahead of yours tonight? Same distance, a slower kitchen night, and suddenly it's a much longer wait.
Last time we predicted one number from another. Today, what if we used 2 numbers instead of 1?
Quick recap. 9 students, a midterm score predicting a final score, a fitted line, y hat equals b naught plus b1x. R squared came out around a third. 2/3 of why finals varied wasn't explained by the midterm at all.
So what's hiding in that other 2/3? A good guess, how much a student actually studied.
Which means, don't just replace the midterm with hours studied, use both together.
Formally, simple linear regression was y equals beta naught plus beta 1x plus epsilon, one predictor.
Multiple linear regression stretches that. Y equals beta naught plus beta 1x1 plus beta 2x2 and so on, up to beta kxk plus epsilon. Same idea, more letters. Every beta still an unknown constant, still estimated by least squares.
Today, we'll use k equals 2, midterm score in hours studied per week, both predicting the final.
Here's the geometric picture. With one predictor, the data is a cloud in 2 dimensions, and least squares fits a line through it.
With 2 predictors, the cloud lives in 3 dimensions, and least squares fits a flat plane through it instead. Same idea, one more dimension to picture.
And the rule underneath never changes. Minimize SSE, sum of squares for error, the total of the squared misses. 1 predictor picks a line, 2 pick a plane. More than 2 pick a shape we can't draw but can still compute. A fresh batch of 9 students, new numbers, same idea as last time. Midterm score, final score, and now also hours studied per week. Midterms from 50 up to 99, hours studied from 2 up to 9, finals from 48 up to 86. Can the 2 of these together, midterm and hours studied, predict the final better than either one alone?
With 2 predictors, fitting the plane means solving 3 equations at once. Nobody does this arithmetic by hand. The software hands back y hot equals 17.41 plus 0.356 times midterm plus 4.30 times hours studied, r squared 0.848.
Compare that to midterm alone. Y hat equals 26.18 plus 0.533 times midterm, r squared only 0.348.
Same 9 students, same target, but the 2 predictor model tells a fuller story. Next, what do 0.356 and 4.3 actually mean?
This is the one genuinely new idea today. B1 equals 0.356. Holding hours studied fixed, one more midterm point predicts 0.356 more on the final.
And B2 equals 4.3. Holding midterm score fixed, one more hour studied per week predicts 4.3 more on the final.
Holding the other fixed. That's the phrase to hold on to. It's what makes 2 coefficients readable at the same time, instead of tangled together.
Let's use it. A new student, midterm 80, 6 hours studied a week. Plug into the 2 predictor model. 17.41 plus 0.356 times 80 plus 4.3 times 6. Work it through and you land around 71.7.
Compare. If you'd only known the midterm score, the 1 predictor model would have guessed around 68.8 for that same student.
Same student, 2 different guesses, because one model simply knows more about them than the other does.
Before we go any further with r squared, let's actually define it precisely. First, SST, total sum of squares. Take every actual final score, subtract the overall average, square it, and add all of that up. That's how spread out the finals are before any model even gets involved.
Second, SSE, sum of squares for error. Same idea, but subtract the model's predicted value instead of the average. Square it and add those up. That's whatever's left over after the model has done its best.
And R squared is just 1 minus SSE over SST. Our two-predictor model had an R squared of 0.848, meaning midterm and hours studied together explain about 84.8% of why finals varied. The other 15.2%, that's the SSE, still sitting there unexplained.
Here's a trap worth knowing about. Adding midterm and hours study together, R squared jumped to 0.848.
Now, add a third variable. Anything, even something silly, say the number of pets a student owns. Pets obviously have nothing to do with exam performance. And yet, R squared still creeps up to 0.859.
That's not a fluke. It's a mathematical fact. Add any variable at all to a regression and R squared cannot go down, ever. Which means R squared by itself can never tell you a genuinely useful predictor from a useless one padding the model.
So statisticians built a version that pushes back, adjusted R squared. 1 minus SSE over n minus k minus 1, all over SST over n minus 1. It divides by the leftover degrees of freedom, so adding a useless predictor actually costs you something now.
Watch what happens with our numbers. Two predictors, adjusted R squared, 0.797. At the pets variable, plain R squared ticks up to 0.859, but adjusted R squared drops, down to 0.774.
Plain R squared went up. Adjusted R squared went down. That mismatches the tell. Rule of thumb going forward, watch adjusted R squared, not the plain version, when deciding whether a new predictor is worth keeping.
New wrinkle. Not every useful predictor is a number you can plug straight in. Sometimes it's a category, a yes or a no. Take a coffee shop tracking its daily muffin sales. Customers is obviously continuous, but whether today is a weekend matters too. Code that as Z, 0 for a weekday, 1 for a weekend, and it slots right into the model. Y hot equals negative 0.84 plus 0.569 times customers plus 3.44 times Z.
Picture two parallel lines. Same slope, so each extra customer sells about the same extra muffins on either kind of day. But the weekend line sits higher up, about 3 to 4 more muffins even before a single customer walks through the door.
A 0 or 1 flag can shift the whole intercept up or down without touching the slope at all.
One more thing worth watching for. Multiple regression quietly assumes each predictor is telling you something the others aren't. Picture two overlapping circles, hours studied and practice problems completed.
Students who study more usually also do more practice problems. The two predictors overlap heavily, telling you a lot of the same story.
When predictors share that much information, the model can't cleanly untangle which one is actually doing the predicting. Coefficients get shaky. Sometimes one even flips sign, even though the model's overall predictions stay perfectly fine. Statisticians call this multicollinearity.
So the whole arc today, same model as before, just more predictors. Same least squares, still minimizing SSE. A plane instead of a line. Coefficients read, holding the other fixed. R squared and adjusted R squared together, telling you whether a new predictor actually earns its place. And categories can join right in, coded as 0 or 1 flags.
And this is genuinely just the beginning of where the textbook goes from here. Chapter 13 takes that same spirit, comparing means, and extends it to comparing more than two groups at once. Chapter 16 has an entirely different toolkit for when the usual assumptions don't hold at all.
One predictor was a start. Today, 2. The textbook keeps going a lot further than this course did. Thanks for building this one with us.